The problem 3.4.10. So the question asks us to verify the Hermite interpreted polynomial for 2 points only. So now we're given the function values at 2 points x0 and x1, and also the derivatives of the function at these 2 points. And the question is to construct a polynomial, Hermite polynomial of degree 3, which agrees with the function f and f prime at these 2 points. Okay, we know from class that this polynomial can be constructed by using the divided difference method. We need to construct this divided difference table so that I use the diagonal entries as the coefficients of our h3, which is parameterized in this way. So that's our h3. Okay, so this h3 function is given by this, and here f of z0 is just, so remember that z0, z1 are both equal to x0, and z2, z3 are both equal to x1, because we only have 2 points, so that's 4 of the z values we need. And then we just get this f z0, f z0, z1, and f z0 through z2, and f z0 through z3. And for these terms, the first one is just the zeroth, the term of degree 0. This has a degree 1, this has a degree 2. Remember that this is nothing but just like x minus z0. This is like x minus z0 times x minus z1, but z0 and z1 are both equal to x0. That's why we have a bar here. And then this is just x minus z0, x minus z1 times x minus z2, which will become just this term because of our definition right here. So the question is why this is working, okay? So to show that this is working, we just need to check that, first of all, we have 4 values, right? We know the function value at these 2 points and also know the derivatives of the function at these 2 points. So in total, we'll have 4 values. And by this, we can construct a polynomial degree 3. So the degree is okay. The only question is why this function h3 defined in this way will agree with the function f and the derivative of f at the 2 points x0 and x1. So the only thing we need to do is just to check that it is this h3 indeed agrees with the f and f prime. So we just need to plug in x equals to x0 and x1, and then take a derivative of h3 and again apply substitute x with x0 and x1 and see what they are equal to. Okay, so first of all, let's check the h3 evaluated at x0. So as you can see, if h3 is defined in this way, then we plug in x equal to x0, then this term is gone, this term is gone, this term is gone. So all these 3 terms are gone. Only the first term is left, and that is f of z0. But by definition, f of z0, if you only have one argument in here, that's nothing but just f evaluated at that point. But at z0 is just the x0, so that's just this. So that means these 2 are equal, which is fine, okay? Which is what we needed. And then we need to plug in x equal to x1 and see what h3 equals to. So when we plug in x equal to x1, we see here that we need to replace this by x1, this by x1, then this by x1, x1. So you can see that this term is gone because the last term has this as 0. And then we only have the first 3 terms left, and these are the 3 terms. And then what we need to do is just expand what these 2 things are and see how we can cancel things, eventually reach to f prime at x1. Okay, sorry, to get the f of x1. Okay, so first of all, this is just the f of x0. This, in the construction of a Hermite polynomial, this is nothing but just the f prime at x0, right? Because these 2 values are the same. Okay, so that's just f prime. And here, this one is constructed based on the f of z1, z2 minus f of z0, z1 divided by z2 minus z0. Okay, and then remember that this is by definition this forward difference here. This is just the derivative of f at x0, and this is just the x. Remember, this is just x1, this is just x0. So we just put it back here, and then we can see we get this. So now, if we look at this part times this, then we can see the denominator cancel. We only have f of x1 minus f of x0 left, and that together with this f of x0 will give us just f of x1. And then we look at this part, And this part, you can see that they cancel. So that's why I only have f of x1 left. So this verifies that H3 actually agrees with the function value f at these two given points. So now we move on to the derivative. So to get the derivative, we first need to take a derivative of this h function with respect to x. So you can see this will be gone, and this will only have this term left, because this taking derivative of this is just giving us 1. Taking derivative of this is just 2 times x minus x0. Taking derivative of this, we need to use the product rule, but that's doable. Okay, so when we take the derivative, we get this. And now let's kind of expand this. So by expanding this, we know that just the f of z1, z2, z3 minus f of z0, z1, z2 divided by z3 minus z0, and this is just the same thing as above, derived using the chain rule, the product rule. And then we can plug in x equal to x0. So now you can see that when I plug in x equal to x0, this term is gone, right? And this term is gone, and this term is gone. So we only have this first term left. And that first term is nothing but just the f prime at x0, right? That's our definition for this. And then we're plugging x equal to x1 into this formula right here. Then we'll get this. Okay. The reason is that when you plug in x equal to x1, this term is gone. So you only have x1 minus x0 squared, and this is just x1 minus x0, so you only have x1 minus x0. One of them is cancelled to get this. And then combining this and this term, we know they are the same, just have different coefficients, so we get this. And now we expand these two things. The first one here is just a 0 f of z2, z3 minus f of z1, z2, but the f of z2, z3 is just the derivative of f at x1. Okay, and expanding this, just giving us this. And then you can simply do some calculations, because this will be cancelled with these things, and these two guys will be cancelled. So you only have f of x0 minus this, which is cancelled, and you have this term left. That's why we have verified h3 prime at x1 is equal to f prime at x1. So this finishes the proof.